Okay, so at the end of the last video, I asked you how to calculate the OLS estimator for the slope. And the formula is simple, covariance divided by variance of x. So covariance is 4.72, variance is 6.36. So, we calculate that. Maybe A. Right, so A is the answer. And then, what I wanted to show you is this one. So what is the OLS estimator for the intercept? Use the formula like here. So pause the video and do some simple algebra. Okay, so let me show you the answer. It's pretty simple. Mean of y, 7.77 minus this number at beta 1 estimator times x bar, 13.10. So then you can calculate that. But what I wanted to say here is the intercept is calculated after beta 1 is calculated. So as I said, beta 0, so what you can see here is if you move x beta 1 to the other side, y bar is the fitted value of x bar. Did I write here or no? So beta 0 is kind of just balancing out the remainders so that the residual has mean 0, right? So relatively the intercept is mathematically not that important. Like slope is more interesting object in general. Anyhow, so this is how you calculate and compare that to the Excel result. The differences are coming from rounding errors. So rounding errors are pretty huge. Okay, so that's that. That is about so far we learned how to calculate the OLS estimators, right? We are minimizing the sum of squares and then it is actually calculated using the covariance divided by variance, right? Pretty straightforward idea. And then the second part of regression, residual analysis is assessing the model, how good your prediction is. And we start again from the residual sum of squares, right? Residual squared sum, right? This is the amount of error in the regression, right? When you predict y, this is the total amount of errors using sum of squares. We are going to do the same thing to different objects, right? So a y bar is just mean of y without any regression. So y bar is, so you are comparing your regression model to y bar. So y bar is included here and y hat is your fitted value. This is kind of like the numerator in the variance formula, right? Variance formula, you do not have hat here. So if you erase hat, this is exactly the numerator of variance. So we are going to call this variation. So variation in y hat, right? So then the interpretation of this guy is the variation explained by the regression. So fitted value varies over observations, and if your fitted value varies more, that means you could explain y better, right? And compare this to this guy. This is exactly the numerator of the variance, total sum of squares. This is the total variation in the original data y. So in this original data y, this is the variation you would like to explain. And what is interesting here is, mathematically, the total sum of squares, SST, equals SSR, the regression sum of squares, and sum of squared errors. So remember, this is unexplained variation, and this is explained variation, right? So we can perfectly decompose the total variation into explained plus unexplained. This is a very interesting idea. And you may think about then, using this idea, you can think about how much you explained out of the total variation. So back to the Excel. Here, I explained this sum of squared, residual sum of squares is here. And you see regression sum of squares is this. And total sum of squares is this. That means, so in your original data, the total variation is 425. 425 is the amount of variation in the original cost, right? But after prediction, your predicted values, fitted values can explain this much variation. 395.5 is the explained variation, but the remainder, the other 29.4 is unexplained variation. You cannot explain, your regression model could not explain this much, okay? So that is 3 different sum of squares, right? Regression, explained, residual, unexplained, and total is total. Of course, some of these two guys must be the third one, the total sum of squares. And here, let me explain what these guys are. DF means degrees. Oh, why it doesn't work? Somehow my keyboard does not work. I don't know. It's delays. So DF means degrees of freedom. So I explained the degrees of freedom as the amount of information. So let's put it this way. There were, so now let's think about, like as I said, the variation sum of squares is the numerator of the variance. And when you calculate the variance, like originally you have 12 information, but you consumed one of them to calculate the mean before calculating the variance. So your degrees of freedom when you calculate the variance is 11. So if you calculate the variance, you have to divide the sum of squares by this number, n-1, to make it unbiased, right? So this is denominator. Sum of squares is numerator, then degrees of freedom is the denominator. Similarly, when you calculate the residual, originally you had 12 information, but you consumed 2 of them because one was beta 0 and the other was beta 1. So now you only have 10 observations, right? Okay. And then here, when you calculate the fitted value, the only remainder is 1 because you used all the information for beta 0 and beta 1, and also you are using x's. So the only freedom is only 1. So you may think it as the difference between these two guys, right? So actually this does not make much sense in this story, but like just you may think that because residual uses 10 degrees of freedom, then the fitted value part only has 1. So it has only 1 line. So in that sense, using only 1 point. So when you calculate, when you divide the sum of squares by something, it should be degrees of freedom, right? So then MS is mean of the sum of squares, mean squares, right? So taking literally it's mean of the squares, right? So divide by sample size, divide by the squared, divide by the degrees of freedom. So this divide by 1 is this number, and this divide by this is this number. So that is how we can interpret that. And so this will be more important when you learn F. Unfortunately, I think I cannot explain these two in this class. So they are important later in the future. I plan to make chapter 13 to explain that, but it's not easy to include that in this lecture right now. Okay, anyhow, back to our slide. We decomposed our variation into explained part and unexplained part. So we So this is ANOVA table. By the way, let me put that. So the name of the table is ANOVA because it is abbreviation of analysis of variance. So ANOVA. So it is called ANOVA, analysis of variance, a very important and famous analysis toolkit. And then after the decomposition, now we can calculate how much we could explain. That is called coefficient of determination, usually often referred to as R squared. So out of total variation, how much we could explain. So the numerator is explained variation. Or equivalently, you can take 1 minus the percentage of unexplained variation, right? So of course, sum of squares are always positive. So this is always a positive number between 0 and 1, right? Because these two numbers are always positive. They always sum to the total variation. So it measures the strength of the relationship, right? So back to the Excel. So we can find R square, coefficient of determination, here. Coefficient of determination is here, and this is calculated as regression sum of squares divided by total sum of squares. So ratio between these two guys is the same thing, right? That is, so you may interpret this as the regression model. In this regression model, 93% of the variation is explained. Okay, that is how you interpret this coefficient of determination R square. Right? This is what we just saw. And another interesting interpretation is the reason why it is called R squared is because mathematically this is correlation coefficient squared. The correlation coefficient between the actual value and the predicted value is R, denoted as R. Then you may think it as R squared. So and of course, if your prediction is good, the correlation will be close to 1. Because always correlation is in between plus minus 1. So its square will be also between plus minus, like 0 and 1. Because after square, negative numbers will become positive. So this will be always in between 0 and 1. Right? So extreme cases, if R square is 0, that means there are no linear relationship between x and y. And in this case, beta 0 is 0. Beta 0 will be perfectly 0. So x does not help explaining y. On the other hand, if R square is 1, that means the correlation is 1. Perfect linear relationship. So all the data points are perfect line, right? So R square can be interpreted very intuitively using percentage or as a squared correlation. So anyhow, it calculates the correlation. So the correlation is correlation between fictive value and the actual value is calculated here. Multiple R, right? So this is correlation between actual values and predicted values. So then let's try this. If you square this, you should get R squared. Same thing, right? So its square of this number is what you see below. And then, what is the adjusted R square? That is a little bit different. It's in this case, in this example, adjusted R square doesn't mean anything. Does not matter at all. But later, when you have more than one variable, later you may include x1, x2, x3. So you may include more variables to improve the quality of the prediction. Then R square formula should be changed. So, typo here. So the R square formula slightly changes to reflect the number of variables, then you are going to use adjusted R-squares when you have multiple independent variables. So for now, it is not that important. I'm not going to explain. That is also related to this part. So I'll just stop here. So this guy is not explained. I will not explain how exactly that is calculated. So as you see, we fill all the results. You learn pretty much everything. Of course, I could not complete these guys, and we'll do that in the future, in maybe next year or so. Okay, so then now let's see the other example. Return to education example. What is interesting here is, like, let's look at the R-square first. R-square is 10% only. This is more realistic. In the earlier example, R-square is 93%. This is very much unrealistic. Or yeah, when your explanatory variables are really powerful, then this is possible. But many cases, 10% is not bad. Because think about this. You are explaining wage only using education. How many factors affect your wage? You are taking only one, that is education, and only one variable explains 10% of wage. So that is only a lot. That is surprising actually. Oh wow. Education is powerful predictor for your wage. Okay, so you have to understand that. But still, you may think you would like to improve that. That is possible by including more independent variables. You would like to include more independent variables like this. Not a big problem. Just add x2 with another coefficient, right? So this is the only difference. Almost everything works in the same way. All the intuition works in the same way. So calculating OLS estimator, anyhow OLS will be calculated by Excel, but the idea is the same. Minimizing sum of squared errors. And maybe the key difference is like this. Beta 1, when you interpret beta 1 now, must be like this. When x1 increases, how much y increases? When x2 is unchanged. So you have to put this condition. When x2 is held fixed, what is the relationship between x1 and y? That is beta 1. It is exactly the economic assumption of ceteris paribus. So everything else being the same, what is the effect of x1 on y? So let's make reasonable assumption. So when you interpret, you have to mention that. It's an important condition. Everything else is pretty much simple extension. Fitted value, simple extension, just include that. Residual analysis, identical. Once you calculate epsilon hat, everything else being the same. Right? Decomposition works the same way. Right? So let me show you data with another variable. Oh, I did not open it yet. So let me open the data. So we have another variable, age. So to calculate, to explain your hourly wage, I am going to include education and age. So the older you are, then you get more experience, then your wage will increase, right? So to prevent confusion, let me call this salary. So your salary is determined by age and education. By the way, when you have 3 variables, of course, scatter plot does not work anymore. Just have a look what happens. So you need to choose 2 variables to make a scatter plot. Also weird. The data are from like 33 and 45 years old. So data look like this. And trend line is actually, it's flat, but rather decreasing, right? So trend line goes like this. But let's do the analysis. Data analysis, regression. Here, in doing this, now y is salary, and x variable is education and age. So you can include just 2 columns, right? I'm choosing all these columns. So then automatically it will recognize 2 variables. And so let's try this. Now there are 2 different line feet. By the way, the problem here is actually when you have 3 variables, your graph must be 3-dimensional. So 2-dimensional graph does not work. It is not linear anymore. So it is not exactly a line. There are some variations, like there are variations within a line. It's close to line, but there are variations because there is another dimension. It is clear from here. Wage graph. So like a age and salary graph, you have variations that is coming from unobserved, like education, that is not drawn here. So when you have more than 2 variables, graph does not work well. Instead, it works fine. So you have all the same tables, but another line, this line is added. Everything else being the same, one line for another variable is included. So all the theory works in the same way. Okay. Now then, this is the last question of this video. Now let's do a prediction. Consider a person whose age is 30 and 16 years in school, college graduate. What is the predicted hourly wage? So try to calculate this prediction and then continue to the next video. Okay, thank you for watching. Next video will be last video, and short. Okay, see you later.